Okay, if I press the undo option, then what will happen is this particular part will be removed and whatever is there on the top, that will be displayed. Think of this as if this is your editor. Okay. So suppose if you do a redo operation, how do you think redo will be performed? Any guesses? For undo operation, you're removing. That's fine. Whenever your text is changing, you're inserting that element into the stack. Okay. Suppose if you want to implement redo operation also, what would you do? I'll give 1 or 2 minutes to think. For undo operation, you're saying, let's say at 30, undo will be reversed. How will you reverse? How will you keep track of those reverse things? Any guesses? Say suppose you have the stack. Let's say after 30 seconds of time frame, whatever your structure looks like, that particular structure you're storing. So first 30 seconds, your structure looked like A, after AB, and then ABC. Now you said whatever is at the topmost, that's the only thing you can immediately pick. Remaining things you can't see. Okay. And then, so when immediately it says redo, you'll go back to the previous 30 seconds frame. To go back to the previous 30 seconds frame, you'll just remove this one. So our structure looks like now A and AB. Suppose from this one, I want to perform a redo operation. This is an undo operation. You want to perform redo. How will you get back ABC from this one? Snapshot at every update, yes. So snapshot, yeah. How the definition of snapshot can be anything. If you want to take a snapshot at every update, or if you want to take snapshots interval wise, anything is fine. Like if you press Ctrl Z, you will pop the top element. Exactly. If you do Ctrl Z, basically this top element will be popped out. Now your element is popped out, but suppose if you do a redo operation, what will happen? Then Control Y, yes, Control Y operation. How will it be performed? How do you think internally? How does that implementation look and all? Then by calling AB again. Lalit, can you elaborate on your answer? Okay. Let's say I maintain one more stack also. And this popped element, I just don't leave it as popped element, but I use another stack to store this. Now I store ABC. Now, if I say redo operation, what I'll do is, whatever the topmost element is there here, I'll put that one back here. So, can I implement this redo operation with two stacks? Okay, great. Undo operation can be implemented with just one stack, but for redo operation, you require both stacks. Okay. See, while performing undo or redo operations, what are the important operations we performed? the topmost element was our important concern, and then we had to push each snapshot, and we have to pop each snapshot. Whenever undo operation is done, redo operation is done, you push back, you pop the things between two stack or single stack. But at every instance, the topmost element is your current state, is the current state of the editor. Okay. So, and do you think any other parameters are important? Say suppose your stack is empty and you're calling a pop operation. You're doing a control Z on this one. What will happen? It will stay in the same state. Okay, but suppose in some internal implementation you have to you should let your system know, okay, this is empty. Even if pop is called, do nothing. Or say suppose your system is full. Okay, your system is full and you're trying to push more and more things. Then also there needs to be upper bound to your system. See, suppose while discussing recursion also, if you remember, we discussed there's something called as stack overflow. Stack overflow happens when you call multiple things, but the space allocated to this particular program or the space of the system gets finished. Then you can't keep inserting things. So the two important terms which we discuss here are overflow and underflow. So overflow basically happens when you push elements exceeding the capacity. Exceeding the capacity, and underflow occurs when we try to pop elements when there are no elements. Stack is empty. So sometimes it becomes important that we check the conditions whether the stack is empty or stack is full. These is empty and is full are also two important functions to make our algorithm or our program know that currently the stack is empty, currently the stack is full. Okay. So what do you think? Okay, suppose if given a task to realize say stack using the data structures or the any kind of structs or any kind of data structures which you have already used, how do you define a stack with all the existing data structures you have learned? Suppose if you're asked to implement all these functions using the data structures which you already know, how will you do it? And remember that top is something which really qualifies a stack. And one more point, if you observe, there is only top element. So whether you push or pop, you do it to the top element only. At the top element or you pop out the top element. So both insertion and deletion in a stack happens at only one end. Deletion happen at one end. So now the task is implement stack functions using the data structures which you already know. I'll give you 2 or 3 minutes to think, then we'll discuss. Okay. Okay. Any ideas? Use linked list. Okay, linked list is one idea. So you try and say, "Ki, this is my head. I proceed, and suppose I have my tail. So do you want head to be the top element or the tail to be the top element?" Tail to be the top element. Okay. So now if I ask to do a push operation, okay, fine. To the tail, I'll attach a next element. What shall we do for the pop operation? Remove tail element. Okay, I'll remove my tail element. But for these kind of data structures, I need to keep generally for me to define a linked list, head is very important. And because I want my operations to perform really fast, let's say I'm using this tail also. Okay. Now adding insert operation, fine. I can this insert operation I can do it in time of one. Now, if I have to move the tail pointer back, okay, what will I do? I will suppose let's not use insert delete terms. Let's use pop and push in. Okay. To push, I can do it in off an operation. I can push an element. Now, to pop an element, how much I mean, what will be the complexity to pop an element from this linked list? Okay, so now my tail has to come back and point to this one. Yeah, so my tail has to I have to rearrange my tail pointer and I have to delete this one. Let's say I have to free up the space and delete this element. Okay, so if I have to reach this one, I can't in a single linked list I cannot reach back. Okay, if I cannot reach back, then I'll have to traverse and then come back. Okay. So it will take an O of one operation. But suppose, let's say if you have doubly linked list also. If you have a doubly linked list, then both the operations can be performed in O of one operation. Doubly linked list we can perform in O of one because you have pointed to this one and you'll also have pointed to previous things. Okay. See, observe few things here. We use linked list because when we want our real life scenario to realize something which is very huge, and if you are very particular about a non-contiguous space, then you have to use linked list. If you're not very particular about a non-contiguous space, but if you're more particular about getting easy access, and see, suppose if you have to create a node. How does a node look? It has to store data, it has to store address. Okay. And this will take up a little bit extra space also because you have to store the extra address. So this might take up few extra space. So if you want advantages like easy access and 1 minute. If you want advantages like get access easily, or let's say, suppose you want to minimally use this space also. Use the space, then we might have to go to arrays. Suppose I have an array. Okay. I define one more variable top. Give me 1 second. Okay, just give me 1 minute. I think it is out of charge or some issue. Just give me 1 minute. So yes, so think of it in terms of, suppose you have an array and you have a pointer which is pointing to the top of the array. Okay, so whenever I want to insert an element, I say top plus plus. Now at this particular index, push the element. If I want to do a pop, I'll just do top minus minus. I'll just move my pointer. Okay. How does that sound? Does that sound a little bit more better than linked list? Think and let me know. Here, if I use a doubly linked list, then only my push and pop operations are becoming O of 1 and O of 1. But if I use a simple array and one pointer, then also my push and pop operations are O of 1 only. Okay. Yeah. Suppose I have this array. Okay. Let's say we have this, it is defined up to some n space. Okay. And initially, let me say my top is -1. Okay. Let's say now I have to push an element. What will I do? Let me say I'll do top plus plus. And then ARR of top is equal to my element. Let the element which I want to insert, say it is suppose X. If it's pop, I can just simply do top minus minus. And suppose if my index is here, I'll move it back here. I don't care what if elements are present, if elements are not present, that's not my concern now. Okay, my stack, for my stack, pop, push, getting the top element are the three most important operations. If I'm able to get that one, I'm fine with it now. Okay, and suppose if I want to get the top element, how will you get the top element? ARR of, you can just do ARR of top, print ARR of top. Okay, see, now you wanted a data structure which has easy access, whose insert operation is easy. In general, for an array, delete operation is costly only. Suppose if you want to delete, then you have to rearrange the elements back again. But here, it's always that you'll delete from the end only. You'll not delete it from the start. Okay, or if you think in terms of C++, you can realize it using vectors also. You can do vector dot pushback. Okay, you keep elements will get inserted. Still, you can maintain a track of this top index. If you want to do, you can do top minus minus. Okay, I mean internal implementation, you can do it at any way. Okay, suppose now I want to check my underflow condition. Okay, what is my underflow condition? Underflow happens when there are no elements. Okay, let's say I want to check underflow happens when my stack is empty. Okay, how will I check whether my stack is empty or not? Any answers? Ashutosh Ankit, yes. If you are discussing about the complexity of the linked list pop, yes. O of n, that's right. Top pointer is equal to 0. Okay. Anything else? High is equal to low. Okay. So while characterizing a stack, we have only one variable top. We don't have anything. If you are able to access top, if you know the location of the top, we can perform any operation. So there is nothing like, we don't have any two different pointers, high or low. We just have only one pointer. So now think again. Can I say when top is equal to -1, my stack is empty? Okay, great. And when can I say my stack is full? Suppose I have defined an array of space n. When can I say my stack is full? Top is equal to n. Okay. Very close, I would say. Yes, top is equal to n minus 1. So basically, top is equal to -1. When I'm at 0th index, my 0th position is already filled. So if my top was n, my nth position should be filled. because I'm starting my indexing to be 0, when top is equal to n minus 1 only, then my stack is full. Okay. Top is equal to n minus 1, then you can't, no more insertion or no more push possible. Or in other words, the stack is full. Okay. Now let's see. Suppose we had to write a user-defined data structure for stack and implement all the functions. How will we do? Let's say user-defined functions. Now, let me say I defined a struct of name stack, and I declare an array of size n, and then I have a variable called as top. Let's say we initialize it to -1 initially. Okay. So I'll just briefly write all the functions which we have already discussed. So let me know whether I'm writing it right or not. That's it. Okay. So let's say we are writing functions for this data structure to implement all its functions in. Okay. Suppose I have I want to check if my stack is full or not. Okay. Can I say return top is equal to n minus 1? If it's true, it means that the stack is full. If it's false, the stack is not full. Okay. Second, bool. Let's say is empty or is full. Okay. Then can I say return top is equal to -1? And if you see, these are comparative operators. These are not assignment operators. Comparative operators return either true or false. So I'm just using a direct return statement. Whole algo. Underflow. Okay. Let me read out. Top is equal to 0, then underflow. Item is equal to stack top. Okay. Top element, then top is equal to top minus 1. Yes. I think you have almost wrote all the conditions for each pop, push, and underflow operation. But yeah, with the data structure or with the struct which I have defined, let me write it again. Okay. Let's say, suppose we have C, and what do we want to do? We want to push. Okay. We need to push an element. So this requires a parameter. You need to pass some parameter. What to return? You need not return anything from this one. Okay. To push an element, first you have to check whether there is any space in this one. Okay. Say if you have called isFull function. If isFull function is equal to true, then you can say no more space to enter. No more space to enter. No more space to enter. Okay. If the full is only when there is a space to fill, only when there is a space in the array which we defined, then only we can insert. How do we insert? We do top plus plus, and for that ARR of top, we assign this X. Okay. Then let's say now we have one more operation. Void pop. Pop also does not take any argument. Our stack is defined by the pointed top. Okay. Suppose if our stack is empty. If the stack is empty, you don't have anything to pop out. So before applying a direct pop operation or top minus, first check whether the stack is empty or not. If is empty is equal to if is empty is equal to true, then print stack is empty. Okay. Else what we can do is, what will we do? Top minus. We have moved back the pointer. And now, what else function do we have? Void. What is the topmost element? topmost element, when you call a function topmost element, you would want to know what is the topmost element. So let's say as of now, default, let's say that our data type, our stack data type is integers. Okay. Suppose here, suppose if E is empty, if the stack is empty, then you have nothing to return. Stack is empty. There is no topmost element. Okay. There is no topmost element. Okay. Else, you can simply say return ARR of the current top. Okay. So, did you understand what I was trying to write? Everything clear? Or if there are any doubts, you can ask. Otherwise, you can type yes. We'll go to the next part. Okay. Can we check underflow and overflow conditions if we use linked list and vector? Okay. Yes, I mean, suppose, let's say we are using a linked list. Our operations are costly, all those things are there. But this particular structure you can realize, that's for sure. Suppose you have a head pointer, you have a tail pointer. Okay. When head pointer is equal to tail pointer, there is only one element left. So you can remove that element. Let's say, suppose just before, the step where your head element is equal to tail pointer, and you said you have applied a pop operation. You can maintain some flags saying ki when head pointer is equal to tail pointer, I have freed up this space. And now my head pointer is a null pointer, tail pointer is also a null pointer. Then when head pointer and tail pointer both are equal to null, then it is an underflow condition. If it's an overflow condition, generally, let's say, suppose if you want to check overflow conditions in case of linked list, generally you say generally in linked list you not face as overflow because to avoid conditions such as overflow, we define the linked list, right? So, but even if our system space is also done, automatically a program will only throw up an error. Or one more thing which we can do is we can keep an upper bound. Say for this program, I require n stack space. If my program is taking more than n stack space, stop it. Then you can keep track of number of elements on linked list. And then you can keep the upper bound or condition on the overflow. And if you are using a vectors and arrays are essentially the same things, right? Here, instead of array, you just have a vector which does not have any bound. If similarly, as I told you in linked list, if you want to keep any upper bound for a stack, you can keep that upper bound for the stack. And similarly, using top, same, you can use the same operation, same thing which we did in case of arrays, but just that instead of ARR of top is equal to this one, we can just use ARR dot pushback. Then element will be inserted. For pop back, you can do top minus. But here what happens is every time you'll not be able to do a pushback because every time you don't insert into a new location. Okay. See, in case of vector, you will be able to push back, but you'll not be able to pop back. Okay. And see, you will not be able to directly pop out that element. You need some pointer to check. But in case of stacks, if you have such a data structure defined, and now if you say, let's say, let me define a stack. Okay. Struct stack S. Okay. I can do S dot push 10, S dot push 20, S dot pop. What has happened? I've inserted 10, I've inserted 20, and I've popped back. Now my the final data structure looks like this. But in case of a vector, you'll be able to push the elements, but you'll not be able to pop out the elements. So the operation which is not available in vector, this pop operation is available in stack. So there are some particular use cases where you'll be able to use stack, but not vector. The internal implementation of stack relies on vector plus some pointer addition. Some kind of pointer variable and your vector. But whereas if you want both the functionalities combined, you can define these functions and directly make use of this one. Ashutosh, yes. Okay. Now, if it's a C language, stack is easy to insert elements easily. Yes. And now, if you observe, whether you're checking whether the stack is full or not, whether you want to push the elements, whether you want to pop out the elements, whether you want to know what is the topmost element, all the operations are O((n) operations when it comes to stack. Every operation is just O((n). Okay. And when are stacks generally used? Stacks are generally used when your data is continuously changing and there are multiple insertion and deletion operations. Okay, and insertion and deletions in this sequence, like last in first out sequence. Okay. When there are multiple instances, multiple instances of insertion and delete, on the recent elements, elements, then stacks are used. Okay. Keep this point in mind. If you want to perform many insertions and deletions, we'll be using some other data structure. We'll discuss later. Okay, just keep this point in mind. We'll discuss later. Okay, when it comes to a C, yes, you have to use user define. So you have to write this struct, you have to write all these functions and then define this variable. But whereas when it comes to C++, yes, you have all these inbuilt functions. Okay, you have a keyword called as keyword called as stack. You can mention what type you want to use and its name. The keyword is struct, this is type, and this is variable name. Then inbuilt, all these functions are implemented for it. So simply you can just do stack int s and you can start using all the functions. All the functions which we have defined now, they're inbuilt in C++ and you can straight up use them. Which one? I mean the C++ part or the previous part which I have discussed? Ankit, let me know which part you want me to repeat. I'll repeat accordingly. Star point. Okay, star point. Okay. So suppose you have some data structure, you have some use case where you want to perform insertions and deletions at only one end. You want to insert continuously, delete, insert, delete at from only one end. If the use case is such, if the use case is like that, then you have to use stacks and queues. I think you are a little bit fast. Okay, cool. I'll repeat this point, no problem. Okay. So if you have some use case, ma'am, handwriting not clear. Okay. I'll rewrite this part, don't worry. Okay. Let me rewrite this one. Okay. When there are multiple insertions and deletions from one particular end, then use stack. Okay. But in general, if number of insertion and deletion operations to the data are more, deletion operations are more, we will use some data structure. Okay. What data structure and all those things I'll discuss. And this is just this is like kind of pointed to the further coming topics. That's it. It will be vague only. Keep it vague. Then after I discuss those data structures, you will be able to connect to this point. Ankit, is that clear? Okay. So stack is defined for a particular use case. It is defined for use cases like this, where you want to delete from the top, enter at the top, access top elements. If the use cases are in such a way, then only stack is used. If you want to delete a middle element from the data, or if you want to insert at the middle or other elements, it will again depend on the use case. Whether you can use, if you want to insert at the middle, suppose you say the address of that particular storage is available. I mean, where you want to insert, then you might use the linked list. Or if the data is sorted, then you can directly make use of arrays and you can delete that element. So again, for each use case, you choose a particular data set. I mean, particular data structure. Okay, great. Ravi Shankar, is that point clear and the remaining point also clear? Okay, let me just write this also. This part also I'll write again. So suppose in C++ you have inbuilt functions. You have a stack keyword, like how integer is there. Stack is also kind of a data type. It's not a data type, it's a data structure. Its keyword is stack. And you mention what type of data you want to store in this data. And then you mention a variable. That's how you define your structs C++. Example is stack int, say S1. Okay, once you define, you can do S1.push an element X, S1.pop, S1.top, access the topmost element. You can check if your stack is empty or not. You can check if it's full or not. This operation is least used. Okay. Rather, there is a function called as s1.size. Okay. There is an operation called as s1.size, where you will be able to know the number of elements in the stack. If you want to keep an upper bound, you can keep the upper bound using size. These are predefined functions. You can straight up define and use these things. But internally, how they are working and all those things, you are well aware. Even if you're asked to implement, you should be able to implement. Because in questions, they might ask you to slightly tweak your stack data structure. Then, for tweaking your stack data structure, these functions won't be enough. You need something from the implementation. Okay. I'll give you a problem very similar to that one after we are done with this topic. Then you'll realize, okay, just not understanding what the definition of the functions it will do, but it is also important to know how they are internally implemented. Okay. Clear till here? No. Easeful is not inbuilt. No. Okay. What about remaining people? Clear? This is about the theory of the stacks. If this is done, we'll move to few problems of stacks now. Okay. Okay. Good. Okay. Good. Now let's say the problem is implement 2 stacks in same array. two stacks in same array. Okay. So you are given some upper bound to the capacity of the array. Okay. Some upper bound is given. Let's say you have a stack. You have an array. It's index 0 and index n minus 1. In a single array, you want to implement two stacks. What will you do? How? Implement two stacks means okay, suppose I'll say there are two top variables, top 1 and top 2. Okay. I might give some insertion operation to the stack, and I might give some insertion operations to this stack. I might give some pop out operations to this, some pop out operations to the stack as well. And if I ask key return the topmost element, you should be able to return this topmost element. If I ask that, also you should be able to return. So basically, I want all the functionalities, but the space is only single array. How do you keep track of tops? How will you push and pop into two different stacks, but your space is a single array? Okay, give me a minute. Yeah. Okay. So did everyone understand the question? I think I got some answers, but did everyone understand the question? Reverse half for the first stack and the other half for the second stack. Okay. So did everyone understand the question, what I was trying to say? Ma'am, I did not understand the question. Okay. So the question is, somehow you have to maintain two different stacks in one single array. Okay. Then maintaining those two stacks, and in those two stacks, you should be able to perform a push operation. You should be able to perform a pop operation. You should be able to provide a top operation. Okay. I say from push the element into stack 1, push the element into stack 2. Suppose if you want a single array kind of realization, what you'll do? You'll maintain one single array. You'll have your top variable here. For push, you'll keep incrementing top. For pop, you'll decrement the top value. And using two arrays, you can realize this one separately. But now what I'm saying is, I'll give you a single array, but I want all these functionalities to be implemented using a single array. implement all the functionalities of both the stacks using single array. Okay. Use pointer to call the top one, top two in the arrays. Okay. You know that the top is something which defines the stack. So where will you place your top pointers is the first question. Second question is, how will you move your top pointers and store and delete values accordingly? Okay. Now if everyone has understood the question, think about it now. Don't know. Okay. No problem. We'll discuss. Okay. Let me discuss. So first method is, I have array. I can realize one stack with one array very easily. We have already discussed. I have one array, but let me say I'll break it into two parts. I have 0, n minus 1. Let's say this is n minus 1 by 2. Okay. This particular start index is n minus 1 by 2. And this start index is 0. I'll place my top one here. I'll place my top two here. Okay. Initially my top is minus 1. Initially my top 2 is n by 2 is the first index. So minus 1 of that one. Okay. Then let's discuss the underflow and overflow conditions for both the things. Okay. What is the underflow condition for the first stack? What is underflow? To check whether the stack is empty or not. Okay. How will I know whether my first stack is empty or not? Yes, top is equal to minus 1. Top is equal to minus 1. What will be my overflow condition? N minus 1. So n minus 1 is here. Okay. This is the space which I have designated to stack 2. This is the space which I have designated to stack 1. My stack 1 and stack 2 should not collide because I don't want a mix up and return wrong elements. Okay. Okay. For stack 2, n minus 2 minus 1 is the starting element, is the index which will be inserting. From this element, any element belongs to stack 2. So will this particular element be my last element of stack 1? So can I write that when top is equal to n minus 1 by 2, which is the starting index of top 2, I don't want my top to point till there, minus 1, the previous index. Right or any confusions? Okay, Sachin says yes. What about remaining people? Any confusion in this? Ma'am, could you repeat n minus 2 part first? Okay, okay. N minus 1 by 2. Okay. So what I did is, I was given one single array. Okay. I have to implement two stacks, but I know how to implement one stack using one array. Even though I'm given physically one array, virtually I have split it into two parts. Half space I gave it for stack 2, half space I gave it for stack 1. I said the starting index of my stack is 0. Of my stack 1 is 0. For my stack 2, suppose my index is still n minus 1. Okay. n minus 1 by 2 is the starting index of stack 2. From this, I'll use this array for stack 2. I'll use this array for stack 2. I mean, this n minus 1 by 2 is your choice. You can do n by 2 also. I did n minus 1 by 2, but it is your call. However you want to split it into two halves, you can split. N by 2 and n minus 1 by 2, only one element difference will come here and there. Okay, after defining, so what are my important, so given a stack, I said I should be able to perform all the operations, all the push, pop, top operations I should be able to perform. Before performing any other operations, the two important conditions are the overflow and the underflow conditions. If you see the push, pop operations and the top operations, we have made use of these conditions. If you have checked whether the stack is full here, we have checked whether the stack is empty. Here we have checked whether the stack is empty. So before writing those functions, I was trying to write the overflow and underflow conditions for individual stacks. Okay, for the stack 1, underflow condition is when top is equal to minus 1, then there are no elements present in this one. That means the stack is empty. The overflow condition. If it was a full stack, we wrote when top is equal to n minus 1. If this is when this is the last element of this particular thing, then we told that is the overflow condition for a stack with singular. But now, as our space have been separated, it is divided into half. I told n minus 1 by 2 is the first index of top 2. The previous index is the last index of stack 1. So if my top 1 has reached that particular index, n minus 1 by 2, which is the start index of stack 2, and minus 1 for the previous index, then I'll say that all the whatever the capacity which I have assigned to stack 1, that is full. Okay, things clear till now? Okay. What is my underflow condition for stack 2? Good. Ashish, Lalit, yes, Sachin, good. What is my underflow condition for stack 2? Okay, n minus 1 by 2. Think once again. Here, my starting index for stack was 0. But when my top is equal to minus 1, then it's an underflow condition. When top is equal to 0, which means that there is an element at index 1. There is an element at index 0. So we have to underflow condition is just below the start index. Yes. So it will be n minus 1 by 2 minus 1. When top 2 is equal to this. Okay. What is the overflow condition? Top 2 should be equal to right, n minus 1. Good. See, once you have overflow and underflow conditions, can you write push and pop conditions easily? Yes or no? While pushing, generally any stack. While pushing, what you have to check is check overflow. If there is no overflow, do top plus plus, and for that array top, assign the element x. Okay. For pop condition, check the underflow condition. If it's not underflow, then do top minus minus. For getting the topmost element, you will just have to do ARR of top. Okay. But there is one very, very slight problem in dividing the array into these two equal halves. What do you think will be that one? I'll give you 2 minutes to think. There is some particular drawback in defining the spaces like this. Memory wastage? Yes. Yes. Memory wastage, how? We first have to define, then we can, first we have to define array size first, then only we can divide. Exactly. In other words, yes. So what's happening is I divided my space into two. Okay. Let's say my operations went like insert element into stack 2, insert element into stack 2, insert element into stack 2. Continuously, I have been inserting elements into stack 2. At some point, I'll reach the overflow condition for stack 2. But still, to the space which was given to me, some space is still left. I'm wasting the space. Okay. Because this is moving in this direction. My one stack is second stack is growing in this direction. First stack is also growing in the same direction. So for both the stacks not to collide, I have put a boundary. But so there could be some better space utilization. So the initial answer, I think if someone has answered, I don't remember. I think it is Ashutosh. Yes. What if our two stacks grow in opposite directions? What if first stack is growing in this direction, second stack is going in this direction? For insert, suppose this is a stack 1, this is a stack 2. For say this is initially my top 1 is here, my top 2 is here. Okay, let's say my top 2 is n. Okay, indexed from 0 to n minus 1. My top 2 is n, top 1 is n minus 1. To insert an element, I'll do top plus plus. Here to insert an element, I'll do top minus minus. Then will there be better space utilization? Yes. Yes. Okay. So then again, let's write our overflow and underflow conditions. Overflow, underflow, overflow and underflow. Okay. First, let's discuss about underflow conditions. Okay. What is the underflow condition for stack 1? Yeah. Okay. Lalit says top is equal to minus top 1 is equal. Let's call this one top 1 and let's call this one top 2 just to avoid confusion. Lalit says top is equal to minus 1. Do anybody have any other answers? Yes. Top is equal to minus 1 is right. What about second stack? What should be the condition for top 2? Yes. What should be the overflow condition for stack 1? N minus 1. Okay. Any other answers? See, let's consider an example. The stack, I said insert one element into stack. Insert some element, insert some element. Now, I can insert here, here. I have inserted elements into stack 1. Can I insert one more element in stack 2? If I'm going to insert one more element into stack 1, basically I'm overriding the values in stack 2. Here my top 2 is there. My top 1 has come till here. N minus top 2. So basically, when they're adjacent, the upper bound for both the things is relative. Based on the other top value, just based on other top value, this overflow condition is going to change. Suppose if I pop the element from top 2, okay, suppose I don't have this one. Okay, everything got erased. Okay, let's remove. I have stack. I said insert 3 in 2, insert 5 in 2, insert 2 in first stack, insert 3 in second stack, insert 4 in first stack. My top 1 is here, my top 2 is here. Okay. Now, at this position, I can't insert any more elements in top 2. I can't insert any more elements into my stack 1. Both the stacks are blocked. But suppose if I do a pop operation on top 2. Okay. Now, this 5 is not there. And my top 2 has moved here. Now I can insert elements in both of them. I can insert element into stack 1. I can insert elements into stack 2 again also. Okay. So here the overflow conditions are relative for both the stacks. So can I write when top 2 is equal to top 1 plus 1, it's an overflow condition. And similar is the overflow condition for this one also. Top 2 is equal to top 1 plus 1. Yeah, n minus top 2, all those things. However you want to define them, you can define them. This is just one convention of writing. Yeah. Coming to Ankit's answer, if my overflow condition was n minus 1 by 2, I would have used this notation only. I mean, both the stacks moving in the same direction. I wanted to do it in one stack in one direction, other stack in other direction, because Sachin did not get it, man. Okay, I'll explain again. Okay, suppose, say, shall I examine the overflow part? Yes, I'll explain. See. Okay. We'll do this example again. Okay. Okay. My first, so my first top is here, second top is here. Okay. This is my first stack top, this is my second stack top. I said insert 3 into second stack. My top will move here. Insert 5 into stack 2. It will move here. Okay. Now, this is my top 2. My top 1 is still here. Okay. Insert 2 into stack 1. Insert 4 into stack 2. Insert 3 into stack 1. All these 3 elements, stack 1 insert operations are there. Okay. Now, my top 1 is here. Let's say my array okay. Out of charge again. Say my array has a fixed capacity of size 5. Now, if I want to insert any other element, I have to move my pointer, and in place of 5, I have to insert any other element. In stack 1, if I want to insert any element, I have to replace 5 value. If I replace 5 value and make it 4, okay, let's do that one. And let's see what happens if we do that. Let's say now I got these are stack 1 elements. I said, now stack 1 dot push. I said 4. Okay. Let's assume that we made that change. Okay. Then top 1 is also here, top 2 is here. Now, if I ask s2 dot top element, technically what will I return? ARR of top 2. My top 2 is at this index. My output will be 4. But what should be the original output? The correct output should be 5. Because I did not check the boundary condition perfectly, as I have inserted an extra element in top 1, I got a wrong answer. So, in such cases, I should not perform this operation. My top 1 should be here only. So basically, when my top 1 and top 2 are adjacent to each other, it means that I cannot insert any more elements. Similarly, here I did an insert. I did s1 dot push. You might receive an instruction on s2 also. They can say s2 dot push 6. Then you would want to move your top pointer, but there is no space because stack 1 has come and occupied till the maximum possible distance. Okay. Now, these are the overflow conditions for the stack. Suppose, let's consider one more case. Okay. I have inserted only one element in stack 1. This is my top 2. But somehow it happened that I had to insert all the 4 elements in top 2. The sequence of instructions which I received are like this. Okay. Now, I'll name the indices also. Now my top 2, this is my overflow condition. I don't want my top 2 to go beyond this. Initially, in our previous example, I did not want my top index to go less than 3. Here, I did not want to go it less than 1. Okay. So the overflow conditions are not fixed conditions. Like previously we had, right, n minus 1 by 2 minus 1 or n by 2 minus 1 by 2. They're not fixed conditions here. They're depending on the relative positions of the top. How many operations are in what sequence you have received the instructions, what are the locations of these top 1 and top 2. Based on that condition, the overflow conditions are dependent. So when my top 2 and top 1 are adjacent, that is when we have reached the overflow of both the stacks. You can't insert any more elements into both these stacks. So when top 2 is equal to top 1 plus 1, top 2 is equal to top 1 plus 1, I can't insert any more elements. And similar, you can't insert into top 2, neither you can insert into top 1 for the same condition. So when top 2 is equal to top 1 plus 1, you can't insert, or this also you can't insert. There will be the respective overflow conditions of stack 1 and stack 2. Such and other things clear now? Great. Okay. Let's do one more problem. Okay. Now, so it's a very, very, everyone might have heard about this problem. Probably this needs no introduction. Valid parenthesis. What is valid parenthesis problem? Okay. So for conditions for valid parenthesis are, if there is an open bracket, there should be a corresponding closing bracket to it. Okay. Second condition is the sequence in which outer brackets have appeared, the closing brackets also should appear in the same sequence. opening bracket sequence should be equal to closing bracket sequence. Bracket sequence in the reverse order. Okay. Let me ask you examples. Is this a valid parenthesis? Okay, this is a valid parenthesis. Then, is this a valid parenthesis? Okay. So you observe what kind of pattern do we want in the question? Opening bracket should occur in some sequence. Closing bracket, same sequence, but it has to happen in the reverse order. Think of stack. What happens? We push the elements in one sequence. While we pop out, we get the same elements in the reverse sequence. Right? So we can realize this problem using stacks. Okay. How do we do that? Let's check. Let me consider this one as a character Ankit. Yes, like this. Yes, that is a valid parenthesis. You have square brackets, curly brackets, normal curved brackets. That's the sequence. Your closed brackets occurred in a exact reverse sequence. So that is a valid parenthesis. So your task is that, given an expression, you have to check whether the parenthesis is valid or not using stack implementation equation. Yes, yes. Okay, let me say I'll iterate through the expression. Let me say this is an expression. This is a character explanation. It can be of any length, so I leave it. Okay. Next, let's say now. Suppose I have, say, this is my expression. Suppose if this was here, there is a curly bracket pushed inside, then there is a curly bracket outside. If my latest open bracket which I have pushed matches with the earliest closed bracket, then I'm fine. Otherwise, I'm not okay. Consider this example. Okay, I have pushed a square bracket open, then curved bracket open. Then the latest opening bracket which I've pushed is a curved bracket. Then I got a closing bracket, but I got a square closing bracket. Then the condition will fail. And I'll say, no, this is not a valid parenthesis. If I received a curved bracket, then okay. I have found its pair. This is fine. And I'll remove this from the top also, because the sequence and the sequence matched. Now I'll wait for the next closing bracket which occurred just previously. Now I'll be waiting for open square bracket, closing square bracket, because after this curved bracket, the immediate one which is in the previous sequence is this one. Okay. Ankit, I think you're trying to ask me a different question. Evaluate this expression using stack, that's right. But as of now, the question which we are discussing is just to check whether a parenthesis is a valid or not. That's it. This is the basic for many problems. You will find extensions of this one throughout. Okay. Man break. Okay, I thought if you complete this one, freshly we can start the cues part. So that's the reason I started this one. But yeah, the idea is this one. Maybe we'll, okay, no problem. Okay, done. We'll start at 2 o'clock. we'll write the code for this part and then we'll move to queues then. Okay, done.